Hey physics students, this is Mr. Gloria coming at you. I hope you're doing well today. We have been kind of just getting started with our unit on energy, Unit 12, and I did kind of want to show you how to use this one kind of simulation. And so this video is kind of there to, or it's kind of here, I'm creating it for you to show you this energy basics kind of sim. And we'll get into that shortly. Now we said there are a lot of types of energies, but there's really only a few types that we're kind of interested here, and one of those types was called kinetic energy, or energy of motion. So when an object has motion or velocity, it's got then KE, or kinetic energy. We could quantify that by taking 1/2 times the mass times the square of the velocity. And I kind of put together kind of an example here, and you've seen this example before. If we have a runner, we know the mass of the runner and the velocity, then we could take 1/2 times the mass times the square of the velocity, and we can get then the object, in this case the runner's kinetic energy. And we always put energy or work, we always basically put that in the unit called the joule. Well, we can also then have this type of energy called gravitational potential energy, and it's basically the energy it has due to its position above some sort of a reference line. So we're lifting basically an object up, and we're lifting it up a certain height above the ground or floor. We give this object GPE, and it takes energy to lift something up against gravity. So basically we're giving that object then GPE, and that's how we quantify GPE. We take mgh, the mass of the object, times little g times the height. And the example we presented on the introductory video, maybe we take a water bottle of mass 1 kilo. We lift it here on Earth, so that'd be 9.8. We lift it up 1 meter. Again, we can multiply those through, and we get a GPE of 9.8 joules. We also then have thermal or dissipative energy, energy lost from friction. And often we might ignore this because we really can't quantify it, or we would like to maybe make the situation a little bit easier and just ignore that. Pretend we're using a friction-free surface, or maybe we'll put the objects maybe on ice where there's still a little bit of friction but not too much. So I kind of want to show you then this computer simulation, and there'll be kind of an assignment on this a little bit later, so I thought it might be kind of helpful to kind of show you what this is and how this works, so you'll kind of be more accustomed to this when you do the assignment. Now there's the link, and I'll make sure to put that link down so you can click on it. But if you want to open up, if you want to just type in under your search bar PHET, Energy Skatepark Basics. I'm just going to hit Control C for me. I'm going to open up a new page here, and I'm just going to put that in, PHET, Energy Skatepark Basics. I'm going to just hit return, and it kind of comes really up to the top, Energy Skatepark Basics. And so I'm going to click on that. And these, again, sims, most of these sims, this one it's written in HTML5, and so we can just run it right off your computer. I'm using my Mac, but you can use your other computer too, a school computer. And we have intro and friction and playground. I just want to deal with the intro, and then I'll show you something with friction here shortly. I'm going to kind of click the intro, and what we have is this kind of skateboard person. And we can change the mass, and we can get these 4 things. I'm going to click onto here because we're going to kind of use this bar graph and etc., to kind of give us a hand here. Well, let me first show you about GPE, or what's called potential energy here. So we've got this grid here, okay, 0 meters, that's my ground, that's my reference point. So right now the skateboard person doesn't have any potential energy. But what I can do is I can lift her up. I can kind of lift her up vertically, and I can give her more and more potential energy. Okay, so let me go ahead and let me make sure it's stopped. So if I put her up here right at the top of the ramp, she's got basically the maximum amount of GPE that she can get on this ramp. You know, if I don't lift her as high, so at 1 meter she's got this much, and if I double that, she'll have double that potential energy. Notice that the total energy always stays the same here. And let me just put her up. So now she has 6 times the energy, gravitational potential energy, she had at the bottom. And notice, using this sort of pie chart, it's all potential. She has no speed. But what we're going to do is we're going to change really her GPE into kinetic energy. So I'm going to kind of click slow-mo and just let it go. For this ramp, we're ignoring any friction, and we're basically not going to have any dissipative effects. So you can see then that we have this sort of oscillation going on between the kinetic and the potential. So when she's at the top of the ramp, as she gets to the top of the ramp, she then has more potential energy because she's up higher. Her kinetic energy is decreased because she's not moving as fast. So right at the top of the ramp, her kinetic energy is 0. But now that as she's at the top of the ramp, and then there's a speedometer, when she gets to the top of the ramp, exactly there, her potential energy is maximized, her kinetic energy is 0, she's got this total energy. Now she's kind of coming back down the ramp. So what we're going to do really is we're changing that gravitational potential energy into energy of motion, or her kinetic energy. So let me so as she goes down the ramp, she's getting faster and faster because more of her potential energy is changing into kinetic. But notice that this total energy never changes. It's a combination or the sum of both of these. So as she gets to the bottom of the ramp, she's maximizing her kinetic energy at the expense of the potential. That's why both of these energies are really based on, motion. This potential energy can be converted to kinetic energy and back and forth. So now her little pie chart, it's mostly kinetic energy. She still has a little bit of height above the ground, but as I forward this to just the bottom of this half pipe here, her now potential energy is totally gone. Why? Well, she's at the baseline. Her height is 0. All of that potential energy now is kinetic energy. Again, the total doesn't change, and we've maximized her speed here. Now, we know that both kinetic and potential energy, we have mass. That's important. Mass is in both of the equations. So really, if I make the skateboard person a more massive person, you could see that she's kind of growing there. I'm going to increase her kinetic, and consequently I'll increase then her potential. Okay, so now our graphs are a little bit higher. Now in this case, we're not dealing with any dissipative effects, but if I kind of go here, I can basically deal with friction, and I can add or have lesser friction or more friction. So let me get these back up here on my chart here. So I've got my bar graphs, I've got my energy, my speeds, etc. So I'm just going to lift her up. Let me make sure it's stopped here before we start. I'm going to lift her up. Okay, so she's got all potential energy. Okay, but then once I let her go, and let me slow-mo it here, once I kind of let her go, as she goes on the ramp, as she moves on the ramp, there's going to be friction between the wheels and the ramp, and that's going to increase my thermal energy. So again, all three, the sum is the total. But now these two, we're going to have less and less of these two, because then the motional energy is going to be, we're going to add into thermal energy every time she goes up and down on the ramp. So she's going to get less high as she then, because she'll have less kinetic energy to be then moved into potential energy, etc. So her oscillations then get lower and lower. Now, that's not what we would find on a friction-free ramp. Friction-free ramp, it would go back and forth and back and forth and back and forth. Okay, but that's not what we're seeing here. So eventually, all of her sort of kinetic and potential is all, basically all dies out, and all that's left then is just this thermal energy or dissipative effects. So let me go back here. So this is a friction-free ramp, and we can just, let me take the slow-mo off. Just do it normal speed. So see, we have no thermal effects. This is a friction-free ramp, and she can go back and forth and back and forth and back and forth. She's never going to lose or have any dissipative effects. Now, the third area, and that you might want to play around with this a little bit before the assignment, we can basically modify the friction and the mass, and we can put these up again, and you can kind of make your own sort of ramp, and you can stack pieces together and just kind of create your own ramp. Kind of fun to do, I guess. So I don't know, I can lift her up, and there you go. So you're welcome to kind of play around with this a little bit. Again, there'll be kind of an assignment using this software, using this sim, and I think it's going to be in that assignment area. Okay, kids, we'll talk to you later. Bye.